CHEM 2211, Recrystallization, Identification of an Impure Unknown. This week we're going to take a heterogeneous mixture of a pure compound and impurities. In this case it's going to be sand, sea sand, that we've mixed in with our pure compound. We've got 8 possible compounds that our unknown could be. And we're going to be using recrystallization to separate out the impurity. We're going to be using melting point determination to identify our unknown pure compound. You're going to be getting all of your data, all of your data points for your table of reagents, your molecular weights, and your melting points. That's going to be the important information for us to have for this experiment. We're going to go through and start off with choosing our particular unknown. We've got D456 ml, and I'm going to write that down on my data sheet. So I've got, here, why don't you come around to this side. D456 ml. And that's what our TA is going to use to determine if we get the right answer at the end of the experiment. We're going to weigh out 1 gram of this heterogeneous mixture. I'm going to mix it up a little bit. Our sand and our pure compound do not mix homogeneously, so we've got to make sure that we get a little bit of both. I'm going to set up my weigh paper so that I can measure this out. I'm just going to fold in the sides to make myself kind of a little dish or a boat to make it easier for me to weigh this out without losing any of my sample onto the balance itself. So now we've got our little catch basin. Lay that down, wait for it to stabilize, and then I'm going to tare so that we're now at 0 grams. All right, let's go ahead and weigh out our sample. Give it an extra stir here just to make sure everything's mixed up. And I'm going to do it in small amounts because I don't want to overshoot my 1 gram. So already we're at about 1/2 gram. Okay, and we're spot on there. So 1 gram and 4 milligrams. Now I'll take this, let's do a close-up real quick, and what you'll see is white crystals with light brown grains of sand in there. So what we see is that heterogeneous mixture. So when we go through the next process of recrystallization, we need to keep in mind the idea that we will not be dissolving everything in this sample. So let's take this out, and we'll bring it over here to our hot plate. And I'll go ahead and pour it into our 125 ml Erlenmeyer flask. I'm just going to bend my weigh paper right in the center. I'll do this in your direction here. And just pour that down into the bottom of the flask. And we can see it down on the bottom there. Does that show up okay?
Yeah, it does.
Good. And this is what we're going to be separating out. We can see our white crystals and our sand particles. Now I'm going to go get about 50 mils of deionized water out of the tap so that we can heat that to a boil. Here's our DI tap. It can be a little forceful, so we got to be careful, be very gentle when you're doing this. This doesn't have to be exact. I'll get roughly 50. Then we're pretty much spot on, so that'll work for us. Take our water back over here. We'll use our 250 ml Erlenmeyer flask as our boiling vessel. And we'll place that on our hot plate. So the idea here is that we're taking two solids that have been mixed together. We're choosing a solvent system that will dissolve one of those two solids, but not the other at high temperature. In this case, the sand will remain insoluble. Our unknown compound will dissolve into our hot water, and then we'll be able to physically separate them via gravity filtration. We'll revisit that once we've actually gone through the process, but that's how we choose our solvent system, is finding something that is able to separate these two compounds from one another based on their solubility at high temperature. So we're going to go ahead and heat this up to a boil and come back. So as we're boiling our water, we'll just make sure that we keep the snorkel above it to catch any fumes or vapors. And then as we start to add our water to our impure mixture, we'll keep them both under the snorkel just to make sure everything is contained. All right, so our water has come to a boil. We're going to use small aliquots of our boiling water to dissolve our heterogeneous mixture in this 125 ml Erlenmeyer flask. Once I start adding the water in, I'm going to place it onto the hot plate, but I don't want to do that just yet. I don't want to accidentally melt our compound before we've gotten it dissolved. Because the flask is hot, I'm going to use one of these three-pronged clamps to help me with pouring. And this is going to be an estimate. We're going to be making an estimate, a rough estimate of the amount of water that we're putting in. And we have to make sure that we use the smallest or the minimal amount of solvent possible. If we use too much of our water, it's going to be hard to get our crystals out once we start reducing the temperature and going through the precipitation process. So let's just pour out maybe 5 to 10 mils. And we'll swirl that around. It's hard to see. Let me see if I can get an angle. Can you see it from that side?
Right, I can now. Yeah.
Okay, so we can see our sand is actually up on the side there. But we're just going to swirl this around. And we're going to set it down on top of the hot plate here. And just make sure that our heat is constant. Now, I can still see a lot of white crystals there. So I'm going to add a little bit more water. I'm going to make sure that all of my pure compound is fully dissolved. I'm going to go ahead and take this clamp off of the flask, and I'm actually going to move this flask back onto the hot plate as well, so we can keep that water hot. I'm going to take a glass rod, and I see a few chunks, white crystalline chunks, and I'm going to try and tap on those to crunch them up, break them up a little bit, making it easier for them to dissolve. Can you see? I'm trying to think of what a good angle would be. So we've still got some white crystalline product in there. Or not product, our pure compound. And then we can see our sand, which is this light tan grains of sand in there. I'm going to add a little bit more of my water. And let it continue to heat. I'm going to leave that to heat for just a minute to see if we can get the last of those crystals to dissolve, and then we'll check back in. So all of our compound is now dissolved into the water that we added to our flask here. We're going to let this heat on the hot plate for a few minutes while we set up our gravity filtration. So our pure compound is dissolved into our DI water. Our sand remains insoluble, so we're going to use a gravity filtration setup to separate the two. First thing we'll do is we'll pour a little bit of boiling water into the bottom of this 120 ml round bottom flask, and that's going to come from our original boiling flask here. And we're going to pour just a tiny bit in there, just a little bit. We don't want to add too much volume. Whoops. And then we'll set this back on top of our hot plate. I'm going to set this onto the hot plate as well to keep it warm. We're going to use our short stem funnel. We'll place just like that. First, I'm going to flute some filter paper so that we can catch our sand. We're going to use the quartering method here. We'll fold our filter paper in half, then we'll fold it into quarters, and then looking from the top, we'll take one of our folds here and we'll pop it out so that now it looks like a cone, and that will fit nicely into our short stem funnel. So we'll see it just like this. I'm going to set a watch glass on top. I'll place that into our setup. Now this has to wait a couple of minutes so that the steam from this water will boil up. It will saturate the filter paper and we'll see some condensate on the bottom of the watch glass. We have to make sure that the entire system is heated so that our crystals won't crash out as they're going through the filter paper. So we'll check back in once that's had a chance to heat up. While our gravity filtration setup is heating up, let's go over to our data sheet and get caught up. We have our unknown code, D456ML. We have our initial weight of the unknown sample, which was right at 1 gram, 3 milligrams. And then we have the approximate volume of solvent used, that was our water, approximately 25 milliliters. Our hot filtration setup, our gravity filtration, is ready to go. We've heated the system. I'm going to go ahead and set it down here on the bench top. I'll take off my watch glass for the time being. And then we have our impure mixture here. Make sure I get that snug. And I'm going to go ahead and pour this through our fluted filter paper. I'm going to hold the filter paper in place initially. And then I'm just going to pour quickly through the fluted paper. And we'll let that filter through. You see a little bit, I don't know if you can see in the flash, you can see a little sort of skin of crystals. So not everything is going to make it all the way through. And I'll go ahead and place the watch glass back on top. And then I'm going to rinse my flask here with a little bit more hot water. We don't want too much. And we can see the condensation on the inside here, so we're keeping that system nice and warm. And I'm going to pour this through as quickly as I can to try and get our sand out of the flask. There we go. And you can see our sand there in our gravity filtration funnel. And that's slowly dripping through. The sand has been trapped by the filter paper up top. Our compound and our water has made it through to the catch flask underneath. I'm going to put the watch glass back on top. Once that has finished gravity filtering, then we'll go ahead and move it to the ice bath. So we're going to make our ice bath. This is to help our product precipitate out of solution. So we have a 400 ml beaker. I'm going to take a handful of ice, go ahead and put it in the bottom, a couple of handfuls here. And then I'm going to add a little bit of water, just to make a slurry. And that's our ice bath. We'll take it back over here to the bench. Once our flask comes down to room temperature, we've got to let it cool a little bit. We don't want to shock the glass by putting it immediately into a cold beaker here. But once we've got all of our gravity filtration finished and everything's gone down to room temperature, then we'll transfer it into the ice bath. So we've cooled our flask down. We're going to go ahead and take apart our filtration setup. We'll get one last shot of our sand that was captured in our gravity filtration. That's our impurity that's now been removed. We'll set that aside. We have our water and pure compound now in the catch flask. And if you look carefully, I don't know if that's showing up, we can actually see some crystals forming already in our cooling solution. So now we're going to take this cooling liquid, we're going to place it into our ice bath and leave it for 5 to 10 minutes to see if we can induce precipitation. As we're cooling down our flask with our crystals, we're going to go ahead and set up our suction filtration setup. This is the way that we're going to isolate our final recrystallized and purified crystalline compound. We're going to need a couple of things here. We've got our sidearm filter flask. We've got our thick rubber tubing. This is our vacuum hose, not to be mistaken with our water hose that we'll see in our distillation experiment. This is what we're going to use to hook to the vacuum. We've got our neoprene adapter, and we've got our Buettner funnel. And as you can see with the Buettner funnel, we've got our opening down here, we've got the barrel of the funnel, and then we have perforations here that allow our liquid to move through. So let's put this together. First thing that you're going to do with a suction filtration is to clamp your flask. You've got to be very careful, because what's going to happen is the weight of this thick rubber hose can actually pull your flask over, and you'll end up breaking the flask and the Buettner funnel, so we don't want to have that. We've got our neoprene adapter. This is what is going to go into the top of our flask. Without this, we can't get a seal, and then the vacuum counts for nothing. We put our Buettner funnel on top of that collar, that neoprene adapter. We're going to go ahead and hook one end of our hose to our vacuum line, the other end to the side arm of our filter flask. We have appropriately sized filter paper. All right, as we can see, that's going to fit perfectly down into the top of our Buettner funnel. When we get ready to filter, we're going to wet that with a little bit of cold water to make sure that it adheres to the bottom of the funnel. We can't get any crystals, or we won't have any crystals moving around the edges of the filter and getting into the catch flask, and we'll be ready to isolate our crystals. So we'll check back in once our compound is fully recrystallized. All right, so we're ready. Let me go ahead and pull this out, show you our crystal formation. We've got a lot of crystals that have precipitated out of our solution here and are ready to be isolated. So we'll go ahead and do the final prep on our suction filtration. I've got some DI water here. I'm going to use a little bit of that just to wet down the filter paper. And then I'm going to turn on my vacuum to pull it through. Okay, and as you can see, we've got a vacuum going here. So let's go ahead and swirl our flask. We want to do this quickly in the same way that we did with our gravity filtration, so that none of our crystals remain behind in our recrystallization flask. Okay, I'm pushing down, I'm exerting a little bit of pressure, and we're letting the vacuum pull our liquid through our filter paper. This can sometimes take a little bit of time, but in the end we'll have our isolated crystals trapped on the filter paper, and our liquid, our water, will go through to the catch flask. We'll let this pull for a little bit and check back in a minute. All right, right, so we've got a good seal. We're pulling our liquid through our crystals. We've trapped that on the filter paper up top, where we can scrape it off in just a minute. Now I still have some crystals remaining in my original flask. So what I want to do is I want to use my DI water. I'm going to rinse through with a small amount of water here, not too terribly much. And I'm going to try and get as many of those crystals as I can into my Buechner funnel. I don't want to leave anything behind if I can help it. So I swirl and then I pour through. Still got a little bit left in there. I'll give it one more rinse. And another quick pour. And there we go. There is a small amount, I don't know how well that picks up on camera, but there's a small amount of crystals, not very much, but that is a possible source of error when it comes to looking at our percent recovery overall. Right? So we think about what may have been left behind in the recrystallization flask. We'll set that aside for now. We're going to let air pull through this Buechner funnel for about 5 to 10 minutes to make sure that we're good and dry before we scrape it off and transfer it to the drying oven. All right, so we've been pulling air through our crystals for a couple of minutes to try and get as much water out as we possibly can. First thing that I'll do is I'll break the seal here at the flask. That's going to release my suction. I'll go ahead and turn it off at the valve here. There we go. And now I'll take out my Buechner funnel. So we've got all of our nice crystals here. I'm going to use my spatula to go ahead and scrape them off of the filter paper and onto our watch glass. Now before I actually scrape these off and put them onto the watch glass, we need to tare the watch glass to make sure we know what its weight is, so that we'll know exactly how much crystals, how many grams of crystals we've recovered. So this is the watch glass that I'm going to use to collect our final crystals. So I need to get the weight of this before I scrape everything onto it. So I'm going to go ahead and make sure that my balance is tared. There we go. Take off the top here. Put my watch glass on. And I'm going to record the weight. So I'll say watch glass is 28.482 grams. So I'll subtract that out from our final weight to get our final product weight, which will go right here. Go ahead and grab this and move back over to the Buechner funnel. All right, our crystals are waiting for us. We've already scraped the majority of them down. Make sure we get everything that we possibly can. This is a very delicate process. You don't want to accidentally rip or tear the filter paper. You want to try and get as much out as you can. As you're going to see here in just a minute, it's not possible to get everything, but we can get pretty close. All right, so there's a small skin of crystals. We've got some dampness. We still have a little bit of water in there, even though we've been pulling through air for a while. So there's going to be some crystal loss as a result of the filtration process. That again will factor into our percent recovery. When you're looking at possible sources of lost crystal weight, this is one of those. Okay, so we'll take these crystals, we'll break them up as much as we can, try and separate them out, and we're going to move them over to our drying oven. Our drying oven is set to 100 degrees. We'll go ahead and set these in. And we'll evaporate off any remaining solvent over the next 5 to 10 minutes. Right, so our compound is ready to come out of the oven. So we've got our crystals in here cooking at about 100 degrees Celsius. Let's go ahead and remove them and take them over to the balance and find out what our percent recovery is. First things first, we've got to make sure that our system is taired. We'll take off the top here. Add our crystals in our watch glass. And record our weight. So this is our product plus our watch glass. And that is 28,738. Okay. We'll go ahead and calculate out our final weight here. Simple math. We've got 256 milligrams of our purified, recrystallized, unknown compound. Now we're going to move on to the melting point determination. So we've determined the total amount of product that we've recovered, 256 milligrams of our purified, recrystallized crystals here. The next step is to find out its identity. We've got white powdery crystals here, and I'll go ahead and write that down under my observations. I'll say bright white powdery crystals. All right, so we're making sure that we've got our observations, visual descriptions, and whatnot. We've got our weights listed out. So we need to use melting point determination to determine the identity of our unknown. If we look back at our table of reagents, I've gone ahead and printed something out here, but these are the melting points for each of our 8 possible compounds. So the first thing that we're going to do is we're going to take a melting point capillary. This is a small capillary tube that is open on one end, and that's going to be open on this end, but closed on the other end. That's very difficult to see, I would imagine. We're going to have our crystals packed into the tube and placed at the closed end. We're going to place them into our melt temp. This is our DigiMelt here. That's going to gradually ramp up the temperature. And once it reaches the melting point of our compound, we'll look through this, this small eyepiece and we'll see the crystals melt. That's going to tell us what our melting point is for this unknown sample. Then we're going to compare that to our list from our table of reagents to make a determination as to its identity. Now this is a multi-point process. First thing that we're going to have to do, because we've got a wide range of possible melting points. We see our lowest is 81 to 83 for vanillin. Our highest is 158 to 161 for salicylic acid. So that's quite a range. So what we're going to do is we're going to do 2 melting point determinations for this unknown. The first is going to be a fast and inaccurate determination. We're going to be ramping the temperature up fairly quickly so we can tell where in that 80 or 81 to 161 range our compound melts. Once we have that general idea, then we'll go back and do a slower, more accurate determination, ramping up our temperature at a much slower rate. That will give us a more accurate determination. Once we've gotten an accurate idea of what our melting point is for our unknown, then we're going to go through and compare our melting points here and do a series of mixed melting points to determine its final identity. All right, so first things first, we've got to get our crystals off of our watch glass and into our capillary tube. We just need a very small amount. And the simplest way to do this is to take the open end of our capillary. Does that show?
Yeah.
Okay. We'll turn it upside down, and we're going to tap it gently into our crystals. And we see that we've got a small amount in the top of the open end of our capillary. Now there's a couple of different ways to pack these crystals down into the closed end, and we're going to look at a few of those techniques. The first is the most basic, which is just gently tapping on the bench top. And because these crystals are so dry, that actually works out fairly well. We've got a small amount in the bottom, but that's not going to be quite enough for our purposes. So we'll go back, we'll tap a little bit more. And we'll knock the rest of these crystals down into the bottom. Okay, we can see that we're getting a little bit more down there in the bottom. And I think we'll do it one more time just to make sure we've got plenty. Now another way that we can get these crystals into the bottom is to use our condenser. Here's our condenser from our lab drawer. What I'm going to do is I'm going to set the tip on the desk, on the bench top, and I'm going to drop this through bottom side or closed end down, and it's going to tap and bounce and tap and bounce. And then when I take it out, you notice that all the crystals are now on the bottom. So that's another effective technique. So if your crystals aren't working their way down the capillary just by tapping on the bench top, you can use the condenser method, and that'll work out just fine. So we've got our crystals in our capillary, and we're ready to do our fast melting point determination. What I'm going to do is here on the DigiMelt, there are 3 lanes here on the top of the DigiMelt. I'm going to put this capillary down into the center lane. And when we look through the eyepiece here, we won't do that just yet. We'll wait until we get everything set up. When you look through this eyepiece, you'll be able to see the crystals magnified. So we'll be able to keep tabs on those crystals to see exactly when they melt. First things first, what we've got to do, again, reminding ourselves that we have our gap here, or our temperature range is 81 to 161. So I'm going to start the ramp up temperature for my DigiMelt at 70 degrees. We don't have to wait from 0 to 70 because we know that nothing would melt before that. So the way that this works, and our quick start instructions are here on the side of the instrument, we'll hit start temperature. I'm going to use the down arrow to take me down to 70. Okay. Then I'm going to hit start temperature again. I'm going to hit ramp rate, and we're going to ramp up at 10 degrees per minute. That's a very quick ramp rate, but we're just trying to get a rough estimate on the very first pass here. And then our stop temperature is going to be 161. There we go. And we hit stop temperature. Set and ready. We'll go ahead and hit start, and we're preheating. Once we get to 70 degrees, we'll check back in. All right, our system has reached 70 degrees. We're going to go ahead and put our capillary in the center lane. You can see it drop down into frame here. I'm going to go ahead and focus on it. We'll do a time lapse for this part of the video, but we'll have this ramping up at 10 degrees per minute. And when we see melting begin, when we start to see that liquid forming, the bubbles of liquid forming, we'll record the temperature and get our rough estimate of our melting point. We finished our fast melting point determination for our first sample. It was 122.7 to 124.8 degrees Celsius. That gives us a good range for our unknown's melting point. We're going to go back and do a slower ramp speed of about 5 degrees per minute to give us a little bit more of a specific or dialed in melting point. So we've already placed that tube in the center slot again. We'll go ahead and focus on that center channel, and I'm going to set my starting temperature. Since we know that our melting point is above 120, we're going to go to about 115. Now let's go to 110. Let's be careful. Okay, that's our starting temperature. Our ramp rate will be 5 degrees per minute. And then our stopping temperature, we'll take it down to about 140. We'll go ahead and hit start. We'll get this preheated. Once it reaches our preheat mark, we'll get the experiment going. And we'll check back in once it melts. All right, we've reached our starting point. We're right at about 110, 109.5 degrees Celsius. We'll go ahead and hit start and get moving with our new slower melting point determination. Just to remind everyone that this sample is once again a pure sample of our unknown from our watch glass. The next phase, we'll be working on our mixed melting points. All right, now that we have our both fast and slow initial melting points for our unknown, we've come up with two candidates that are close in terms of their melting point ranges. We've got benzamide on the right-hand side, and we have benzoic acid. We have to do what's called a mixed melting point determination. We know that impurities, just like our sand or anything else that would be an impurity in a pure compound mixture, will depress and broaden the melting point range of our compound. So what we're going to do is these two potential candidates for the identity of our unknown, we're going to take a little bit of our unknown sample, and what is on each of these watch glasses, this is a little bit of benzoic acid, this is a little bit of benzamide. We're going to take a small amount of our unknown, place that on the watch glass, take equal parts of our known benzamide, in this case, right? We're just going to mix them together, and we're going to add them to a single capillary tube, just like we did before. Tapping it on the desk, however you'd like to load it, whichever technique that we used. And this gives us a mixture of our unknown and benzimide. If our unknown happens to be benzimide, then I essentially will just be mixing benzimide with benzimide, and we should get the same melting point range that we got initially. So we'll set that aside. Now I'm going to take, actually I'll take a fresh spatula. I don't want to mix these two. Then I'm going to take, and I'm going to do the same exact thing. Oh, I guess I already had a little bit right here. I'll do the same thing with my benzoic acid. Tell you what, I'll just bring it over from the side here. Mix these two together. Take another capillary. And go ahead and load that. Now that we've mixed up each of these and prepared these mixed melting point capillaries, we'll place them into our DigiMelt and obtain the melting point range for each one of the capillaries. We're going to put our benzimide on the left-hand side. We're going to put our benzoic acid mixed melting point capillary in the center lane. And we're going to go ahead and set these to melt. We're going to ramp up slowly, 5 degrees per minute, and we're going to watch for their melting point ranges. We'll go ahead and hit start. On the left-hand side, our benzimide and unknown sample mixture, we're starting to see a little bit of weeping, a little bit of liquid formation here. The melting has begun at around 86 degrees. We'll have to keep an eye on that to see when the sample is fully dissolved or fully melted. We see continued evidence of melting on the left-hand side. Additional bubbles starting to form around our solid as it melts. So far, the center lane has remained solid, has not melted. Starting to see weeping in the center tube at about 122.7. Solid is slowly melting. Fully melted at 124.2. So we finished our experiment. We're going to go back to our recrystallization data sheet. We've got our unknown code, D456ml. We've got our initial weight of roughly 1 gram, 1 gram 3 milligrams, approximately 25 mils of water used to dissolve our initial impure mixture. We recovered 256 milligrams of our product. So remember that when you're going through and writing up your lab report, you need to make sure to calculate your percent recovery. We don't know what the initial mixture was exactly because it was a heterogeneous mixture of sand and pure compound. So there isn't really a good or bad yield that you can calculate, but you can calculate your percent recovery based on your total grams recovered, or milligrams in this case. We had our initial fast melting point determination, 122.7 to 124.8 degrees Celsius. We did a slow and more accurate melting point, but it still came out to be roughly the same, 122.8 to 123.9 degrees Celsius. We used that range to help us decide what compounds we were going to choose to do our mixed melting point. Remember, our mixed melting points were used. We chose 2 compounds that were in a very similar range, had a very similar literature melting point range. We mixed some of our unknown with that known compound, benzamide and benzoic acid. When we mixed with benzamide, we got 89 to 107 degrees Celsius as our melting point range. Benzoic acid, 122.7 to 124.2 degrees Celsius for our melting point range. We'll use that information to determine what the identity of unknown D456ml is. Good luck writing your lab reports. If you have any questions, be sure to ask your TA during your Zoom meetings this week.